If
Okay, great. Thank you very much. I hope everybody can hear me. I'm really sorry for missing this actually second conference. I do have a slightly better excuse this time, but it's really a shame I couldn't be there. I really kind of believe in building this bridge between mechanistic interpretability and some of the more statmic things that phys4ML community has been doing. But next year I'll be more around. I'm starting a sabbatical in Perimeter, so hopefully I can get to the East Coast with less uh, in a way that less depends on Trump's state of mind at the moment. So let's go on with some substance here. So this is about um, our kind of attempts somewhere between vision and attempts. I the file had several names on the computer of combining ideas from the renormalization group, which is a very kind of important and profound kind of pillar of theoretical physics, and deep learning, and seeing sort of what kind of perspective it may give us, how applicable it is, and it's I mean, I'll try to have a mix of both. There will be some gap between the two, some vision, and then some of the technical things we know how to do, which are obviously a bit less impressive than the vision, but maybe they can maybe together, maybe some point in the future they can be combined to something more applicable. So here is the outline. It's a bit of a long talk, so first I'm going to describe something that may have been many of you may have seen before, like the general connection of why we think about deep learning as a field theory. And then I'm going to talk like a very basic primer on RG from sort of a condensed matter or StatMech perspective. Um, Hopefully, this is not the first time you heard about RG, but even if so, I hope that some of the basic principles I can convey here. Um, and then I will go on to machine learning, talking about some empirical evidence for phenomena that we usually associate with RG. And then I'll gonna kind of go down to kind of very basic toy models where we can actually start, trying to kind of calibrate this framework from physics and see where it can fit. So this is then these two parts are kind of our first attempts to really make this connection, or at least build one concrete connection, which can kind of be called a renormalization group. Then, for some of you who have heard that, in time permitting, I'll also discuss something that's also about scaling, but it's more about fine-tuned scaling. And it's a recent work we put out um, discussing what sort of it means in terms of fine-tuning budget to grok an algorithm. And I think there is an interesting criteria there to be explored theoretically and empirically. Um, Okay, so let's start with thanking my collaborators on this. Um, some very preliminary work on this line was already in a work with two students of mine back in 2019. Um, and then we had two more concrete works recently. Um, okay, deep learning is a field theory. You can also check out our review if you like. So what's the deal here? I thank Noah for this animation that you see on the right. Let's take the simplest neural network. We can think of a two-layer or two-trainable layer Earth network fully connected. And just for simplicity and just for illustration, let's think that the input is in 2D. Doesn't matter, but makes it makes movies easier. Um, and now we kind of think about some stochastic initialization, a stochastic training protocol. Maybe we're thinking about Bayesian. So in some sense, the weights are random. And if the weights are random, for every set of random weights, we get a random function here. And we can see what happens when we just let these weights kind of travel like a stochastic process, like an Ornstein-Ulbach process within a quadratic potential. We get these kind of fluctuating surfaces. And when we really talk about field theory and deep learning, we are interested in how these kind of membranes, which can sometimes also represent the output and some inner degrees of freedom like pre-activations, how do they fluctuate? How do they match themselves to the target? And you can already see some differences here, which is this doesn't look like your classical fluctuating membrane. It seems kind of sort of rigid in a way. It's moving in a very correlated manner, and that's because the theory is not local. But we can still put that aside for now and remove that. Okay, anyways, yeah, now it's gone. And what we think about as a kernel or as a two-point correlation, as a kernel in deep learning would actually be the Green's function when we map to a field theory language. And many people have discussed this kind of correspondence, and I'm sure actually even prior to this. Yeah, so that hopefully wasn't too painful. And then I just want to flash out, this is not very important. Maybe just kind of remember the first equation. If there are any field theorists in the audience, I just wanted to flash out some of the field theories we find. So for instance, the top one, which I'll get back to later on in the talk, this is the field theory you get. More or less, I kind of suppressed replica indices here, but this is the field theory you get when you think about Gaussian process regression and you average over all draws of data sets from a certain measure. Already this thing, which is maybe the simplest learning model, almost as simple as linear regression, already that gives you something kind of interesting from a field theory perspective. As you have this in our action or in our energy, there is now this nonlinearity, which we would go back to later on. But you can also do that in the feature learning regime. So Noah and I have, and also Itai, have studied two-layer neural networks having this action. We now have a project studying this kind of action. So there is a lot to do here in terms of understanding the peculiarities, the approximations that are valid for these field theories. And that's all about field theory. If anybody has any questions, please ask. And if not, let's go to RG. So RG is an important tool, which was, I think, first used in the context of field theory by Feynman and a bunch of other folks. Got the Nobel Prize in 1965 for QED, where they were able, using notions of RG, to escape all the infinities that are involved in the field theory of QED. And then Wilson got another Nobel Prize on it in 82. And yeah, so RG in the physics world is something that, a theme that's going to come back is this triangle I want to kind of focus on. It's something that connects power laws to scale-free behavior of our observables and to universality, which is perhaps the most profound aspect, which I'll try to get into now. So I want to explain what is this RG in a nutshell. So, you know how it is when you learn something and you don't understand it for a year, and then finally, you read a book that you like and it all clicks, and then you say, oh, it's so simple. If someone would have just explained it to me like that, I would have understood it all. But it never works like that. This is only your, it's your own bias. So I feel like this really summarizes things, but it probably doesn't. So again, I mean, it explains everything, but might be a bit undecipherable, but let's try. You have a complex system. If you are a physicist, think of an action. If you are a statistician, think about a probability distribution with many, many variables. It's very non-Gaussian, non-simple. Everything is correlated with anything. You want to calculate some averages, you're stuck. You don't know how to do the integrals. It's complicated. So there is kind of a greedy approach to solving this. Sometimes you can recognize that even in this complicated probability, there are some random variables that fluctuate in a very mild way, that they are very energetic from a physics perspective. And they're so energetic that you can sort of say, let's think about them as a weakly fluctuating quantity and kind of marginalize over them. That might be simple than doing the whole thing. So what we do is we take our probability distribution and we marginalize in physics over the degrees of freedom with the highest energy. And these are typically the shortest scale oscillations we have in the time and space domain. And once we do that, we formally get a distribution P prime, which has a bit less variables, but contains exactly the same physics or exactly the same statistics for these remaining unmarginalized variables. Now, if we are close to a scale-free point, and we just sort of marginalize over the shortest range, so the highest resolution, if you like to think about an image, and this is an image of something that's like a fractal, something that's very scale-free, then in some sense, P is close to P prime. And later on, I will say in exactly what sense, but intuitively, it should be the case. And so we get a sort of as long as we're close to a fixed point, to a scale-free point, and we are just gradually removing degrees of freedom in a very, always kind of removing very few degrees of freedom out of very many, then we get a continuous flow in the space of probabilities. And this flow in the space of probabilities often converges to saddle points or to fixed points, for instance. So here I denoted some fixed point P star. So this is an approach, a strategy to gradually, if you want, marginalize or compute observables. It's not necessarily easier than just going ahead and computing the observable, but there is some magic to that. And here's the magic. Often, because we're removing these high energy degrees of freedom, they're often so stiff that you can sort of remove them perturbatively. Anytime they appear in a different term, you can say that this is very close to zero. So that gives you often what you cannot do perturbatively in some nonlinear term you have for a general expectation value, you can do perturbatively for these high energy degrees of freedom. So marginalization is often easier than brute force computation of a general observable. So that's kind of an analytical benefit. But here is a more conceptual benefit. Let's say this flow in the space of probabilities, it's a very high dimensional space. So obviously, some mathematicians in the crowd may raise an eyebrow, but let's kind of imagine that as a finite dimensional space. I have now a flow that converges to a fixed point. Then any initial P that I had sort of washes away the information I had in any specific starting point. I could start from here, 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 here. All of these would converge to the same point. That means that I get some universal answer. Basically, low energy observables, or the stuff that I didn't marginalize over, behave very much the same, even if the original probability distribution were starkly different. So the high energy modes can do something crazy, very different, but eventually the low energy modes, the one that are left after I repeat this process many times, behave the same. And this is a very convenient thing for theorists and leads to very strong observation, because it tells us that, an experimentalist would come, in my condensed matter hat, say an experimentalist comes and says, listen, I have this system and I have these atoms that have 6 states and they're arranged in a hexagonal lattice, but I also have a periodic potential on this and I'm seeing some phase transition. What is it? So it turns out in physics that there is such a high degree of universality that in such a system, as long as it has a Z2 symmetry, we know exactly what the phase transition would be, even if we don't even know what the microscopic model is. And that's something that's, of course, very attractive to theorists, because if we need to track any little detail in the problem, and if any little detail counts, our chance of actually doing something, saying something meaningful theoretically, diminishes. And then, okay, maybe another thing to say, this was the case of a fixed point that's completely stable from all directions. But in physics, we often use fixed point in this context also for saddles. So places where if I'm exactly at P star, I would be stable, but if I move in some directions, actually I get a runaway flow. In these cases, we're still kind of good because we are not completely universal, but we can collapse all the data on my original P to these relevant directions that push me away from the saddle. So these would be called the relevant parameters in the theory, and there are often O of one of them. So I can still take a very complicated system, and all I need is to discover maybe experimentally what are two parameters there, and I can tell and I can give predictions. So this is RG in a nutshell. Flow of probabilities, fixed points. This flow is kind of changing the scale of the system, integrating short modes into large modes, and it has some sense of universality. And now I want to kind of look at these. This is a very, so all of this kind of hinges, we can often do RG only when we're close to a scale-free point. And at least in the natural world, and that's the empirical observation, these things are very, very common. So this is a river somewhere in Brazil, I think. I took it from fractals in Google Earth. You can see, that this has a self-similar structure. This is maybe the most remote example. This is turbulence. Okay, so what you see here is a big image of turbulence and then a zoom out and zoom in, and the zoom in looks exactly in terms of its statistical property like the original thing. This is the Ising model at the critical point. There is actually a movie here that I think doesn't work, but this movie actually shows that each one of these things that looks statistically the same is actually a sub-image of the others. And we're going through actually 4 orders of magnitude here. Let's see if it would work. It didn't work yesterday. They closed that video down. Sorry, I should have fixed that. But yeah, this is, but these are different levels of zoom on the same image, basically for the Ising model. And when you have this scale invariance in a stochastic system, it automatically means that all observables you compute have to have this scale invariance. And so that automatically implies power laws. So if I now take the expectation value over all such configurations of this statistical system, they have to declare as a power law because that's the only scale-free function I can have. Okay, so power laws and scale freeness are intimately and simply related. But then there is this notion of universality, which I mentioned, but let me kind of mention that again in this more specific setting. If you take the classical Ising model, which I hope all of you know, and if you now add all small local symmetry respecting perturbations, or if you look at the liquid-gas transition, water to vapor, at the tricritical point, or if you look at many quantum systems with a 1D symmetry, these are all starkly different microscopical systems, but it turns out that the correlation of the symmetry breaking observables has the same form for all of these 4 systems with exactly the same scaling exponent 1 over 4. And that's wow, this is like a pillar of condensed matter and statistical physics, right? The fact that we don't need to care about all the microscopic details and we can get a very beautiful answer like this, which is, it's actually enough to find one exactly solvable model in this universality class of models. And you can use that to compute the 1 over 4, and then you can argue away why the perturbations of all other models are irrelevant to the universal behavior, and you get that. So it's a very powerful statement. And if you want this in a bit more details, that's a bit more for folks who've seen that. So in physics, we often like to view probabilities as actions. So we take the negative log and define that as the probability. And this Ising model I've showed you is actually in the same universality class as this continuum model, model that has this mass term, this gradient term that wants F to be largely the same, and this interaction term. And you can now, when I calculate the flow of probabilities, it actually translates simply into a flow of these 2 coupling constants that I have here, M and U. And this is a very known, very famous flow pattern that governs most phase transitions, most standard phase transitions. So we're going to get back to a similar action when we talk about, machine learning. So you're going to see that graph again. So let me just kind of say what it means. The lines here are as I zoom out on the system more and more. Okay, so I'm taking a spin system, I'm blurring the resolution of the image, and I'm zooming out, so I get another image that looks of the same size, and I'm asking how does the statistics behave as I do that for my ensemble of Ising spin configuration. And F should be thought of as the average magnetization on some not huge but mesoscopic, some finite but big region. And what I get here is the following. If I start with U equals 0, so this is a Gaussian theory, I stay within a Gaussian theory because marginalizing a Gaussian is a Gaussian, and I just flow to larger mass. So I get a theory that's gradually more and more short-range correlated, because if this is very strong, then it's really like white noise. F is just covered by white noise. But the minute I have a finite U, I'm flowing somewhere different. And there is an important line, which is if I tune U and M squared in the right way, then I'm flowing exactly to what's known as the Wilson-Fisher fixed point, and a lot is known about that. And this is exactly a phase transition. So if I tune very properly M squared and U, I would exactly flow along this line and reach the same universal physics, and that's the Ising phase transition. If I push myself a bit in any direction, U or M, I would either go here and here, and I would start flowing somewhere else. Okay, so that's a flow. This is the universality class of the Ising transition. And what you can also see is this has a stable direction and an unstable direction. This has only unstable directions. But if I sort of reverse the flow, and instead of zooming out, I would actually zoom in on a system, then actually this becomes a stable fixed point. The Gaussian fixed point becomes a stable fixed point. One other thing you can ask, okay, well, why is this kind of a sufficient model? Maybe I can add something to it. So for instance, one can add a F to the 6 interaction V. The point is that when properly defined and you remove the lower moments, this extra interaction is sort of boring. It always flows back to 0, so you don't really need to model that. So even though there is some level of knowledge that you need to know to understand where you're on the flow, it's only important to know what's M squared and U, and it's not important to know what is V. And that's what I told you earlier, that if you have saddles or fixed point with unstable directions, you don't need tons of detail. You just have to know where you are along the unstable directions. So that's a really convenient modeling thing that we have going for us. So these are good things. These are all very, very good things. Okay, these are all things that we would love to have in the theory of ML, but nobody says we should have them. So I'm gonna now focus on the empirical phenomena in ML that suggests that maybe similar mechanisms are at play. Okay. And again, if there are any questions, just to see that everybody's with me, please feel free to ask. We have plenty of time. Okay, so when we get to ML,
there's a question.
Yeah.
Can you elaborate precisely which states you mean that's the flow from the Gaussian to the Wilson-Fisher point to the phase transition? This kind of, it's not of the usual kind when you think of the phase transition and thinking of something that is fundamentally very different, I would say. So what are you thinking out there?
So I heard only bits of that. So we were talking about the Gaussian fixed point, and why is that related to a phase transition?
I can get close to the computer so you can hear me. Can you hear me?
Great. Awesome. Yeah.
Okay, so no, I was just wondering, what do you mean precisely by the flow from the Gaussian to the Wilson-Fisher fixed point being a phase transition? Because the things I associate to a phase transition usually are quite different. So
yeah, great. So think about your original Ising model. If you want to tune a phase transition in the Ising model, we have to tune a parameter like the temperature, for instance. Okay, we can also tune maybe the bond strength or something like that, but we need to tune one parameter. Unless we fine tune that parameter to exactly the critical value, we're not in a phase transition. You know, in the Ising model it would either be completely ferromagnetic, which means that everything would flow to everything would just be the same, or it will be completely disordered. So here you kind of see the same thing. You should not think too directly about these m squared and u as parameters of the original discrete binary microscopic Ising model. It's just that as you tune your temperature, you're somewhere going along some curve here.
Okay.
Okay.
No.
And in most places, if you're on this curve, you're just going to flow to maximum positive energy, maximum negative energy. One direction gives you actually the ferromagnet, because if you flow to maximum negative m squared, then you basically get this double well potential, and you get to freeze at this. If you flow up, this is just very, very strong, and you're close to zero, but you're not seeing anything spectacular. But if you hit the critical temperature is exactly at the point where your microscopic model sits somewhere here. It's not exactly Gaussian, that's an idealization, but it sits somewhere along this line. And then it would just not flow anymore. At some point, it would hit this spot, this sweet spot, and then it wouldn't change anymore as we change scales. And that's kind of the hallmark of a critical point. Critical points in physics are, at least second order critical points, are scale free. And that's what we get here. Does that make it? Is that more reasonable?
Yeah. I think I was confused because I had in mind basically a theory of a self-interacting particle. So I think you have in mind like an empirical theory. So okay, I think I get it.
Okay. Okay, good. If there are any other questions, please feel free to ask. Yeah, in a way, it's kind of self-interacting, but it's not really a particle. It's maybe I've written here dx, but actually for this to work properly, you need to be in 2 or 3 dimensions. So there are, but if it was 1D, it's sort of like a self-interacting particle. Okay, good. So when we go to ML, all bets are off. You guys know about power laws, neural scaling laws, and inference time scaling laws, and there are a lot of these things, kernel spectrum scaling laws, but it's not at all clear that all of these things that are kind of go together in standard physics would go together here. But let's just show some cool empirical observations. Okay. So first, power laws are abundant in natural data sets. And that's something that when I first saw, I said, I started in physics, I never expected anything that clean to emerge from the frequency of letters in Tolstoy's War and Peace. It's not even the whole English language, it's just, the translation of Tolstoy to English, okay? And then, so let me just be very clear about what's written here. Many of you have seen that. I take all the words, I count their frequency. That's what's written on log scale here. And then I arrange them by their rank. So rank 1 would be the most frequent word, rank 2 would be the second frequent word. And for every word, for every rank, I write the frequency. And then on a log scale, that behaves as a power law, which is very, very close to 1. Okay, so that's a very nice fit. So that's Zipf law. Another related thing, if I look at the spectrum of simple neural networks, convolutional neural networks, etc., on CFAR10, that's from Yassaman's et al.'s paper, then at least for as long as I can expect for the finite data set I have, there is quite a nice straight slope of kernel. Here it's the cumulative kernel eigenvalues, but it's more or less the same thing. There is a nice slope of the kernel eigenvalues as a function of their index. So I diagonalize my big kernel metrics. I get eigenvalues 1 to the size of my metrics, and I treat sort of the eigenvalue as I would treat the frequency in the top plot, and I get power laws, which is nice. So power laws are abundant in real data. And if we think about neural networks as something that processes real data, it's plausible that it would be that since it's kind of inferring something on a quotation marks critical power law system, it might be sort of critical of power law or amenable to RG as well. maybe I just want to say as a side, I was looking at these things and I was kind of pretty amazed, and I thought to myself, wow, this means that maybe language is a critical phenomena because I don't know, evolution tuned our brains to the edge of chaos and all of that thing. Could be that this is the reason, but there is a more simple explanation for these things. And at some point, we were looking to combine these data models with, but you can have a very simple data model that crudely gives you this power law and might explain also some stuff about why we're seeing power laws in LLM and why this doesn't mean that AGI is upon us. And so just imagine the following simple model. Let's have a random language. Okay, and so we have a distribution of words, and let's just make two rules. Longer words are more rare by some factor. So any word of length L plus 1 is a bit more rare than a word by a factor than a word of length L. And all words of the same length in the vocabulary are equally probable. Okay, so let's see what that gives us. So the first word is the blank word. I just put it here. This is what this means. That has some frequency F0. Then I have two words of, let's say my vocabulary here is just A and B for simplicity. Then I have two words of length 1. This is A and B. And if I choose this factor to be 1/3, then they sit in the frequency scale here at 1/3. Okay? And I have two of them. Now, how many words of length 2 I have? Well, I have 4 words. Their frequency is 1/9. And this goes on, so on, so forth. And the surprising thing is that the curve that passes through the center of these kind of degenerate state is a power law. How can you see that? Well, just think about this image now on a log-log scale. On a log-log scale, these guys, the distance between this line, and that line would be equally spaced. And on a log-log scale, the distance between the center of these two and the center of these two and the center of these 4 and the center of these 8 would also be equally spaced by spacings of log 2. So I would get a straight line on a log-log cloud with exactly a slope of log 3 over log 2. And that's the general. And so, of course, all this is a nice result from by Lee, 1992, that random text exhibits zip law. And also, in a nice way, you see that the general result is that if you have a vocabulary of size m, then the exponential decay is log m plus 1 over log m. So it's very close to 1, consistent with a lot of the power laws we see. So this is a bit of a side, but just when you think about AGI and all of that, and you see, like, let's say that neural scaling laws, pre-training scaling laws would proceed indefinitely, it doesn't necessarily mean that the model is learning something profound. It's just that if I believe that just longer tasks are harder, but there are many more of them, and the model is gradually memorizing them, even such a simple thing would give me a power. And indeed, also the fact that power laws are not indicative of AGI is also from somehow hidden in this paper, because they are showing power laws coming from GPR, which is definitely not capable of AGI with reasonable amounts of data. And just to say, this logic can give generalized to images. You can say words are kernel features, length is like frequency, etc. So, but this is really not central. I just wanted to flesh it out to just say that there is hope that we can even crudely at least understand where these power laws and the data come from, and that might help us later when we build our G on top of that. And this was all about data, but of course, neural scaling laws are famous, became famous since LLMs seem to progress very nicely along these power laws. What exactly are the power laws is a bit debated now, but there are some. It's pretty well accepted that they are there, and so a model being trained as I give it more data and I do another things seem to follow a nice power law. So this is again kind of suggestive of RG. So I have power laws, but does it mean that I have a universality? So that's not at all clear here, but there is some indication of universality in deep learning. this is from the same work. They compared the power law you get for a transformer to the power laws you get for LSTMs with different layers. And at least the LSTMs with more layers seem to sort of follow the same trend. They're a lot worse, but this is just a constant. So if I remind you about the Ising model, the statement also there wasn't that all models behave exactly the same. It's just that all models had the same power law. The coefficient could have been different. So this is an interesting indication that a model that has more or less the same structure, but not the exactly same microscopic details, has some features that seem very much to match. So it could be very, this gives us hope that this slope here is something more universal than the details that go into the particular transformer being used, etc. And if that's the case, we have a chance to understand that. Another reason to believe universality is that, neural networks work. It's not that I need to fine tune every little detail, and otherwise I get horrible performance. A lot of the time we would tweak a lot of things just to get 1 or 2% better performance. So zooming out, this is still a very reasonable model that's sort of robust to small changes. Of course, sometimes these 1% are important to some people, but this is, theoretically, we have bigger fish to fry than these 1-2% stuff. And in some sense, hyperparameter transfer protocols, they assume also some universality between small models and big models. So we have this empirical fact behind us. And so we can now start asking some of the questions that led us to these two projects. Is there some more robust argument connecting power laws, which are abundant, to universality in deep learning? This is one big question. Yeah, there isn't. There was a thumbs down. I don't know. Okay. Does anybody have a question?
No.
Okay, if questions or comments are most welcome, so it'll be a lively discussion. I don't mind as long as okay. Okay, so and then is there a scale associated with power laws in data and learning? Because what is short range, what is long range? In physics, we have this idea of zooming out. Here, we don't have that necessarily. And if there is some notion of universality, what are the minimal models we can study? The reason everybody is grinding the Ising model to death is not because people are just interested in the particular model of spin, because it represents a universality class and it's a very convenient model for that universality class. How can we adapt RG from Phys to ML? Can hyperparameter transfer amount to something about identified tree level scaling dimensions? These are kind of more specific questions, but I get you. I guess you get the gist of it. Yeah. Okay, so now we are going to start making steps to get these notions of RG from physics to learning. So it's so sort of unclear how one would define things, that the first thing we want to do is really get like the simplest setting possible, and that's what we started with, Anindita and others, and Jessica. And so let's take it as a starting point. Just trust me that that this is the action we should care about. At some resolution here is set a removed replica indices. What this represents is the action governing the average output of infinite width network in the lazy regime with a kernel K. And the only reason this is not trivial is that I have finite amounts of data. And so when I average over all potential draws of data sets, I'm actually getting a nonlinearity in the game here. Okay. And so to get things a bit closer to what we had before, I can use the fact that I can diagonalize this kernel with some eigenbasis. So I have some basis of features, phi k of x, and I have the coefficient fk. And then I can write this action in the following way, okay? And now I'm going to use this previous observation that we had, which is that kernel eigenvalues follow a power law distribution. So they go as k to some minus alpha. Here I have these inverse eigenvalues, so they go as k to some power alpha. Now, and I have this interaction, which is a local interaction, which is a bit ugly, but you know, it's an interaction, it's local. And this really looks like how a kinetic term would look like in the Fourier basis, right? If you, I think I have a comparison here. If I take the Ising model and go to the Fourier, to the momentum basis, to the Fourier basis, this is how it would look like. This k square comes from the nabla square I have. And if I, and this was my interaction, here I get something that's quite similar. I have here this k and this, and I can also massage that a bit more. There we go. And take out actually, what just happened? Yeah, I can take in and out some of the terms here. Yeah, and write this, and this way where this is my interaction. The reason to write the interaction here like this is that now it would vanish at large t faster, because at large t, this would cancel this, and this would be zero. So sort of t now controls the strength of my interaction. And to first leading order in 1 over t, I just get a massive theory, very close to this, only there is a discrete summation here. And my interaction is local, but it's not of the phi to the f to the 4th term, it's of this kind of weird shape. But it's actually a very good shape. I mean, it gives very nice physics. Okay, what's similar? There is a different power of k. Here it's a general alpha, here that's 2. That doesn't look like a too big of a deal in terms of the machinery of RG. That's not something we're too afraid of. There is a different local interaction. We can maybe handle that. There is a discrete summation over k, whereas here there is an integral over k. So for those of you who know that stuff, that's like the difference between a finite system and an infinite system. But usually, you know, this is also something we sort of glance over in physics. We say, okay, if the system is big enough, I can just as well do my theory on an infinite system. Where things actually differ substantially is really in this somewhat misleading notation that k itself is not momentum. Okay, and so we really cannot associate this with any local term, and that would matter a lot. But still, it's sort of, you know, 3 out of 4. Let's go ahead and try and see what we can do. So here is what we're trying to do. We're trying to track basically the RG flow of this thing, meaning we're going to marginalize over. This generates a probability. E to the minus of this S is a probability over all these FKs. We're going to integrate out the largest Ks. These are the most energetic modes that we have. And we're going to try to see how doing that affects the other modes. And there's more concrete questions than to ask. Can we do that analytically? If we do that, how many parameters would we generate? Would we stay roughly with the same theory, or would we start generating f to the 6th term, f to the 8th terms, and gradually get something that's completely untractable? So these are all things that are crucial when applying RG in physics. How do we relate the RG flow to the learning curve? Is there universality? Are there fixed points, etc.? So these are the questions we set to look briefly in these things. But there is already here a choice of how we perform RG. We perform RG by integrating out the low-lying modes of the kernel, the low-lying spectrum of the kernel, which in this action, these are the high energy modes, because this is the inverse eigenvalue of the kernel. So this is again the procedure. We have our theory that's written abstractly like this. We're going to always integrate out one mode and see what's the resulting theory on the rest of the modes. What we're not going to do, which is actually an important step, but we left it out in that work, is we're not going to zoom out and rescale. So usually what one does in RG, and that's about comparing this P and P prime I mentioned earlier, is that after one integrates out, one has a theory that where the maximal allowed K is smaller, and then we sort of rescale all of Ks. Okay. So here we're not going to do that. And what's happening here? Okay. So the claim is, well, yes, we can do that. And something quite beautiful happens that's aligned with things that Cengiz and Kanata and Blake found, and works of Bartlett on benign overfitting, and also with some things that we saw, which is that doing this thing, basically taking that theory, integrating out this mode, and tracking carefully the important effects that it has on the other modes, you can repack the resulting theory as exactly the same theory with a renormalized value of T here. This T, by the way, I haven't said that earlier, that's the ridge parameter in the GPR. So if you started from a model with a, say, very small ridge parameter, which corresponds to a very nonlinear term here, actually after one step of RG, you're doing a bit better, because you the original T gets renormalized or gets augmented by the variance of all the modes that one has integrated out. So it's a very intuitive answer. Basically, what's happening here is that when we do this RG, the variance of all the high energy modes, these would be the modes that are very hard to learn in GPR, actually acts as a source of noise for the remaining modes and renormalizes the ridge parameter. And this effect was obtained by other means, in a not exactly this form, but in a very similar form. But it just shows that it can be interpreted as a renormalization effect. Basically, integrating out basically generates observation noise, and these models nothing other than that, which is a very simple and nice answer. And then you can use that once you integrate it far enough, you basically get to a regime where T is so large, the effective T is so large that you can Taylor expand and compute things. And this is what we've done here. Okay, maybe I'll show the results and then I'll go back to this. So just to show that you guys that this thing works. So this is experiments on CFAR and MNIST. These are the experimental lines. The two curves are our approximation and Cengiz spectral effective ridge theory, which is sort of state of the art. And you see that these things are very close. By luck, somehow here we're doing a bit better. I don't think it's something fundamental. But if you don't do that, if you do like the simplest brute force approximation, you would get something very different. So just to show that there is a strong effect here of nonlinearities, but we capture it very well using this simple approach. Yeah, any questions up to this point?
What's the simplest approach that you mentioned that doesn't work so well?
Yeah, great question. So the simplest approach is just take this action with the original T, not the T that you have, and just keep the first order Taylor expansion of this. So once you expand in this, you basically get a quadratic model, and you can compute averages. So this would be the high ridge or high temperature approximation here. So that's what we're preparing with.
Thank you.
Okay, so not to overload you, I'm gonna skip this thing. Yeah, so this numerical result. So focusing on least on the two first questions that we had, can we track the RG flow? Yes, it's very simple. It just results in a renormalization of the ridge parameter, which I just called here kappa squared. Previously it was T. How many coupling constants did we need? We needed one. And you can compute the learning curve here by a very simple argument, which I'm not going to go deeply into for the sake of time. But two important questions remained sort of unanswered, maybe the most interesting questions, which is there some form of universality? And within the framework we had with Jessica and Anindita and Ro, this was an ill-posed question. And the reason goes back to this very fact that we basically integrated out the modes and we got a theory with less modes. So there is no way these two theories can match if we didn't rescale things. So I didn't think it was such a big deal at the time. I went to Moritz, a friend and a colleague, and who likes also doing kind of more heavy algebraic lifting, and I kind of posed that problem to him, and we thought it would be a cool thing. Probably shouldn't take too long. It took a year and a half, but we managed to do this rescaling. And what you get basically when you do the rescaling, it's something very conceptual. Then you can start. Then you stay in the same space of probabilities. You cannot compare a probability on a million variables with a probability on 1,000,001 without sort of, defining some notion of how you squeeze them or put them on the same ruler. So this rescaling step is very important in physics and also here. And we also wanted to do something a bit different. So we actually focused on a case where we are actually in the large ridge limit, but we add to our loss something that loosely represents the effect of finite width, like a perturbative f minus 1 to the power of 4 correction. So what you can think about this as just a different loss function. Instead of MSE loss, I have here this MSE loss plus this term where if u is negative, it actually forces you to get some binary distance from y. If u is just very strong and positive, it just forces you to be a bit closer to y. So this is the toy model we have here, but our point was then to ask really this question. This now looks very much like the Ising model, apart from the fact that I have y here. If I put here alpha equals 2, this looks like a discretized kinetic term of the Ising model. This looks like a mass term, and this looks like a f to the fourth interaction. And there are works out there that actually show that, argue that based on this similarity and kind of similar notion, this would lead to Wilson-Fisher fixed point, etc. But there are subtleties, important subtleties, crucial subtleties that make this not the case. So in a way, the surprise in what I'm going to show you is that this doesn't behave at all like an Ising model. Okay. Despite its sort of similar appearance when alpha is equal to. And that there still is some universality, but in a slightly weaker sense. So as said, the problem really is this non-locality, the fact that although this looks like the kinetic term in K-space when you do Fourier transform, it doesn't imply that these interactions are local, and that puts a lot of problems in the game here. And what we did, and another thing is, of course, this discretization. So the moment K are discrete, there is no way I can rescale them and match two theories, because now it's this rigid grid. So the first thing we did, and that took time, we wanted to find what we call the auxiliary theory, which is sort of a continuum approximation. Think about a kernel that's maybe non-compact or something that leads to a continuous spectrum, okay, rather than discrete modes. In some auxiliary imaginary kernel like this would actually be an integral. And what we wanted is to write down a continuum theory in this fictitious momentum K, where we know how to map expectation values of this theory to expectation values of that theory. And it turns out that this is at least one way, and we think the right way to do that, to write this theory in these terms. So small u became capital U, but other than that, it's supposed to be the same thing. And where things get tricky, and that's where the deviation from standard Ising model lies, is that apart from the y's, of course, is this part here. Basically, instead of a local interaction where I would integrate over momenta and I would have sort of fk, fk prime, fk double prime, fk triple prime, and they would have to sum to 1 from locality, I get this weird interaction, which is completely non-local in K and also is scale full. I have here specifically, I need to integrate the second k prime, from the lowest integer below the current value of k up to that plus 1. So that introduces a specific long distance scale here to the problem, which is 1. So my vertex is scale full in RG terms, and also there is no locality. You can handle that. Thanks to Moritz and Gorka, you can derive a nice flow equation for the parameters, which is not that different from the actual flow equation of the Ising model, with only one main difference, is that things depend explicitly on the scale you're looking at, which is something that doesn't happen in usual RG flow. Usual RG flow is unaware of the scale which it's coarse graining. Here there is an explicit dependence on scale, and that's really the main change. But let me first tell you now how some stuff we can do with this flow equation. So if you get this flow equation, how is it ever useful for you? So here's the procedure. This scale R basically is proportional to P. And that really reflects the scale of learnable modes. Modes where the energy equals P over T, that's this R here, become learnable. So the first thing you do is you integrate out all the unlearnable modes, which means in RG terms that you integrate until R reaches the scale of your cutoff. So physically, that's like integrating out all unlearnable modes. Once you do that, you get an action with very large coefficients, because this is at the scale of the cutoff, and this can reach the scale of the cutoff. So it makes a lot of sense to do saddle point analysis on that. And because this depends on the number of data points P, the larger P is, the less you can integrate. The quicker R would reach the scale of the cutoff. So there is kind of a dual picture here where data sets the cutoff on integration, but also it means that more data probes more high energy properties of your field theory. So at larger data, we're closer to the cutoff, to the UV behavior, to the unnormalized theory. And with small p, we integrate out more, we flow with these equations more, and we become more normalized. So first thing I just wanted to show you is that you can use this prescription and these flow equations to compute some properties of this theory. Somehow the x-axis is missing here. This is k here. So I'm calculating here delta k is a function of fk minus yk. This is simulation. Blue is our prediction. Orange is just naive GP computation that ignores all interactions. And dash black is linear order perturbation theory. So what you can see here is that, it captures something, that's far from GP and well beyond linear perturbation theory. So that's just a technical result that shows, that we hopefully got the equation right. But the second more profound lesson here is that because this equation depends explicitly on how far we coarse grain on this L that signifies that, it's actually wrong to look at it in a 2D plot. It's actually a 3D plot that has another axis of L, which actually completely invalidates the Wilson-Fisher fixed point. So there is no Wilson-Fisher fixed point. Okay. What does remain is the Gaussian fixed point. Okay, so it is still true that if I reverse the flow, I flow to the Gaussian fixed point. These equations predict that. So this is one lesson, and this is kind of something that, maybe it's a bit of a stretch given the simplicity of the model, but maybe hints at something bigger. Because of what? As I make P larger and larger, I go more and more to the UV theory. So in a way, increasing P is like going against the flow of these lines. I'm probing the theory closer and closer to the bare parameters. And what this thing is telling you is that if you start from a theory at low P, which shows significant non-Gaussian effects, basically the interactions are important, the finite width effects are important, and you just push the data more and more in your infinite width model, eventually you're going to flow back to the Gaussian GP behavior, okay, in these models. So that's that can be argued with, obviously, but it's maybe suggest something that's related to Sutton's bitter lesson and all of that, that at large enough data, it doesn't really matter what your model is because it's so forced by the data that all models would behave essentially similar. So I would say if there is some lesson that universality might be possible from our approach, it's this one. It's not universality at low data. It's actually that as we put more and more data, different models like the transformer and LSTMs might actually converge to have similar universal properties, similar power laws and exponent. But at low data, they would be very much different. So this is something that we saw here, and this is one example of that. Yeah, and hyperparameter transfer, I think I'll skip, so maybe I'll have some time for the final thing. So let me just summarize what we understood and what we hope to understand. So as I said, we can track these RG flows. We can actually show that some of the scaling dimensions you get from the RG scaling dimensions, for those of you who know that, you can associate with every field an operator, a naive scaling dimension. Then you just measure the scaling dimension of your loss operator, and that predicts the learning curve. So there are a lot of nice things, that if you dive really into the formalism, you can kind of enjoy. Is there some form of universality only at large P? And then this brings us to interesting questions. Is there sort of a minimal model that captures the large T behavior of more realistic networks, finite width networks? This can point us to maybe a useful toy model. And generally, can we use this machinery to understand how this relation between scaling laws in the data or power laws in the data and power laws in inference in more complicated models. And there are some things about hyperparameter transfer that we can also do, but I left it as a side, so I won't delve into that now. So I think I have probably 10 more minutes left. Okay. So let's just talk about something that's a bit different, but maybe some of you would find that interesting. So if you lost me and just heard RG in the past 30 minutes, this is a good time to wake up. Yeah. And then so this is something we recently put out, and here is what we are kind of asking ourselves. So we've been kind of looking at transformers and trying to teach transformers algorithms, teach them to sort, teach them to do induction heads, teach them to find whether a string is present, maybe teach them to solve shortest path problems. All of these things have been done before in the realm of NAR, kind of neural algorithmic alignment. And one thing you see, and I don't know, maybe some of you would resist, but would have a different viewpoint. But transformers, all of these things, they are not good out of distribution. The reason we have so many employees in all of these companies, which are increasing exponentially, is because we need a lot of data, we need a lot of training, because every time you tell a transformer, listen, you try to teach it how to add 3-digit numbers, it does it perfectly, then you give it 6-digit numbers or 4-digit numbers, performance degrades. Okay, and this happens on, and this is also something that's been seen in much more simple supervised setting, which, out of distribution is hard, it's difficult. The model rarely learns something that's as useful. But on the other hand, we know that it does, in a way, learn useful stuff, for instance, induction heads, right? So induction heads are clearly sort of an algorithmic-like thing that the model has learned. But it turns out that even if you take a model that has learned induction heads on strings of size, on a context of size, I don't know, 100, and you let it try to solve an induction head question on something that's size of 1,000, performance is going to degrade because you have effects like attention dilution. The positional encoding needs to be refined for these larger contexts. So we're in a bit of a problematic point. We want to discuss, what algorithms a transformer can or can't learn. But algorithms like induction head is sort of a search and copy algorithm. Algorithms are inherently, in my mind, an out of distribution question. right? Because learning an algorithm is exactly learning how to perform the task for all input sizes. Okay, otherwise you can just memorize things. There is no complexity theory. There is no nothing there. So we want to kind of quantify how well or what can transformers learn, but we have a problem that they always fail out of distribution. So, and if we are in distribution, we never know, without doing mechanistic interpretability and trusting it, we don't know if they learn the algorithm or just a heuristic that brings them to 99%. So here is kind of the idea we put forward here, but that's kind of the motivation. But here's the idea we put forward here. Instead of hoping to do out of distribution generalization, say on an induction head, that's where you increase the context compared to the training set, let's just ask the following question. How much fine-tuning budget do we need such that the model with context length 1,000 performs as well as our trained model, which was trained on a context length of 100? Okay? And it turns out that these things seem to behave kind of nicely in terms of their scaling. And what we suggest is that whenever this budget, fine-tuning budget, is logarithmic, meaning that it's log of the out-of-distribution task size, problem size, over the trained task size, this is sort of more or less the best you can ask for. And it's also not that bad because it's logarithmic, and at least as a physicist, I don't see a big difference between, a logarithmic and O of 1, and then from O of 1 to 0, it's not a big difference either. So it's a bit, in a way, it's a pessimistic view because it takes the viewpoint that O of D is impossible. I think that, I don't think it's impossible, but it's just to point out that current learning technology often fails out of distribution, but it doesn't mean that it doesn't learn an algorithm. So we want to have a bit of a more relaxed criteria, which has a chance of working for us. Otherwise, so it's sort of a lower bar to properly learning to solve the problem, but it splits problem interestingly into solvable and not solvable problems. So here are some problems. So these are with different rope encoding. This is a string matching problem. I'm going to explain what I did here. I've trained the model here on what is that, on context of size 50 to identify a string of length 2 and tell me yes or no, is this string available? So training was done here. And then I'm asking here, how much budget do I need? How much sample budget do I need when I fine-tune that trained model here on 2 orders of magnitude larger problems? Okay, and on a log-log scale, this is roughly a straight line. It's bounded by a straight line. Okay, which means that basically the budget is logarithmical. I would argue that this is a signature that the transformer has done the best thing it can do, has learned the algorithm, although it will be interesting to match that with MEC-interp studies to do that. Roughly similar effect happens to induction heads. Again, 2 orders of magnitude. I've trained a model on T equals 50, and I'm going here up to 6,000. And although there is some trend on the lines, it's not a pristine slope. It's quite nice that you just pay this linear thing as a function. Soon you will see what happens with harder problems. Then you'll see that this is paradise, really, what you see here. So the point here is that there are models which roughly show logarithmical adaptation budgets, and they seem to correlate, not full correlation, with problems that have simple circuits. I would just make a note here that if you take sorting, which also has a simple circuit, then without repetition, it behaves like this. With repetition, it doesn't behave like that. You get here a linear slope, not in a log-log. Then you say, okay, let's look at harder tasks. For instance, recognizing formal languages, mean cut problem where you embed the graphs in the problem size, and then you see something very different. It's not only that this is nonlinear, it's that this is not a log scale anymore. Okay, so here, you train on a problem size of 10, you get to as good performance as you like. Here I took 10%, you can take it down to 1%. It just costs a lot to do that. The transformer has learned in distribution to have a very good test accuracy. But as you try to adapt that, this is the best logarithmic fit that you get. You actually have something that's concave. You basically have polynomial adaptation budget, maybe even exponential. This was just too expensive. Here it's already heavy training. So this is around probably around 1 billion epochs of extra data points that you add to the problem here. You see the original thing was 3 million. And it's the same thing for a very deep transformer and for a shallow transformer. So it's not an expressibility issue. It really rarely is. And so what I'm putting forward here a measure of a sort of a largely empirically verifiable measure of what it means to have learned an algorithm just from the perspective of the loss and the adaptation budget. And it seems to correlate with things that have simple circuits. And it's kind of motivated by this. And yeah, and that's all I wanted to say. If you want to hear kind of about FIS for ML type work, conferences, job offers, we have this mailing list, which I welcome everybody to join. It's run by Moritz from Jülich. And then you can mail works, and we already have, I think, 250 plus people there, so it's growing nicely. And yeah, thank you for your attention.
Yeah, if you have questions, ideally come close to the.
Zohar, thanks for coming. Yeah, so in the last example, I think you said that these are finite depth but infinite networks, infinite width, I'm guessing.
And okay, so this is an actual experiment, so I can't do infinite width, but here they are sort of wide enough and deep enough to express the algorithm. So stuff that, for instance, that people have done in this NAR literature is they showed, that a transformer layer can learn to do the proper algorithm. And here I have enough layers compared to the depth that I can express the solution. Later on, we have some theory stuff, which is actually about infinite transformers, finite depth infinite transformers. But I don't want to go into the theory too much. I think there are some nice things to do with this logarithmic adaptation budget and theory, but I'm just sort of putting that forward as a measure of, I don't know, adaptable scaling, of some sense, an indication that the network has learned something that's beyond a heuristic. Okay. I think because it's an attainable bar or loosely attainable, it might be something to work against and try to improve the ability of networks to achieve this kind of adaptation scaling. And it's not that simple. For instance, as I said, sorting with repetitions, despite the fact that the network can probably reach with some tweaking that, I haven't been able to get this to follow these lines further away. I got it to follow these lines initially. That was our original primpit, but actually when you scale this up in another order of magnitude, it breaks. And I've tried a lot of things. So there is some criteria here that's attainable, but it's not easy to get to.
When you say simple circuits, do you have like a notion of simplicity, like, RASP walks or like spectral bias walks or anything like that?
No, I'm thinking RASP. I'm actually thinking about some circuit you could write down. Typically, for instance, if you have a circuit, it would be based on some attention, a circuit that does it properly. And then, for instance, if you increase the context length, you would get attention dilution. But fighting attention dilution is not that hard. You just have to scale your scores logarithmically with the context length. And because they're in the exponent, you can suppress the dilution effectively. So part of the motivation for this log scaling was some mathematical works, but also just this fact that if you already have a running circuit, often just increasing the size of the weights there by some logarithmic term is enough to capture a much higher context length. And I think this is what we're seeing here, that there was some circuit like that forming, and it was just fine-tuning itself very mildly based on the adaptation budget. Whereas here, we basically have the model learn a bunch of heuristics that are only useful for the training set for in distribution, and then when it goes out of distribution, it basically can just as well forget everything that it learned, and it's like a new problem. So you get a huge adaptation, a big adaptation budget. But yeah, but doing some mechanistic interpretability on the models that show this behavior is something that I'm keen to do. I'm unfortunately not. I'm not very proficient in that.
Maybe you could speak more about your thoughts on how these step-based kind of tools and ideas will relate to mechanistic interpretability. You kind of hinted at in various times.
You're talking about what, about the RG stuff? Sorry.
Yeah, RG stuff and also this complexities.
So like a more generalized, or I didn't hear the beginning of the question, like a more general.
Yeah, like your general viewpoint on how the RG and stat physics point of views can help or talk with interpretability efforts.
Yeah, no, so yeah, I was fearing this kind of question. I know that this is very much, yeah. Let's see. So, I mean, what we're basically, I think for this we need a better interpretation of the data. But let's say we start from just a simple model. So all the models we analyze here, in all of these guys, all the exact solved models are just these power law models of covariance matrices. So I have rarer features, less rare features. They fluctuate less and more, and then what you basically get here is that, yeah, I mean, as you learn P, what's happening in the mechanics of learning here, and it's not about the dynamics, but more about the sample, the effect of sample size, is that all the modes you can't learn are basically being integrated over effectively. You don't care about them because you're barely constraining them by the finite amount of data. And these are all the sharp features in the kernel. So if I think about PCA images, so it's right. So you do PCA, you get these kind of things, right? So all of these modes here are basically getting integrated over, and they sort of generate a more blurry image on which your actual effective model is trained on. So perhaps by understanding better what are these low-lying modes in the context of, I don't know, language, for instance, these might be synonyms or something like that, some superpositions of synonyms and stuff like that. We can understand, we can sort of try to understand the model layer by first understanding how very weak and stiff feature, very rare features probably are, how marginalizing over them, how that leads to higher order features now. So I think in some sense it should be about understanding these low level features. They should be simple somehow. This is also what happens in physics, right? The high energy modes are in a way simple because the electrons or whatever are so energetic that they barely see each other through the interaction. So they're sort of decoupled. So hopefully there is a set of decoupled features also here in this language example. This is what happens. And we can first kind of easily integrate those out and then sort of understand what's their effect gradually. And so we can kind of reduce the number of things we have to think of. But more kind of more true mechanistic interpretability connections, for instance, relating that to circuits. For instance, are there some circuits that are like weakly fluctuating and I can sort of integrate them out and they just, that will be interesting. The theory is still very much in the realm that's still close to GPR. So what I think about as features are not circuits or pre-activations here, but really kernel eigenmodes. But there might be something, yeah.
So if there are no more questions, let's thank Zohar for the talk.
Thank you very much. Thanks for the invitation.
We'll be back in 10 minutes at 11:30 for the next talk.